Swayam Prabha. Digital India. Educated India.
Welcome to the second lecture on constitutive modeling of piezoelectric materials. So, in the last lecture we saw various approaches to model the constitutive relations, and we started with electrostatics. So, today we will continue our discussion on electrostatics. So, we will start with Gauss law today. It is a very important law. So, it says that if I have this electrical constant epsilon 0 and multiply that with del dot electric field, that gives me the total charge, and this total charge is summation of total charge within the volume, that is the summation of the bound charge and free charge. So, this is called free charge. Now, our dielectric material does not have free charge, so it is 0, but to be more generic we are writing this. Now, this, as we know, we saw it in the last lecture, that rho b can be written as minus del dot p and plus rho f is here. Now, I can take it to this side, and finally, we can write del dot epsilon 0 multiplied by electric field plus the polarization vector p, and that is equal to rho f. Now, this quantity gets a name and we call it electrical displacement. So, this is d is our electrical displacement. And in the integral form, this law can be stated as d dot ds is equal to total free charge. So, it is total free charge enclosed. Now, if we assume that electric field is weak, and then polarization P can be assumed to be proportional to the electric field. So, we can write this. So, where this is called electrical susceptibility. So, this tells us how easily it can be, how easy or how difficult is it to polarize this material. Now, we can combine these definitions and write the vector D as 1 plus susceptibility multiplied by the electric field, and then we can give it a name, and this we can call permittivity. So, finally, our electrical displacement D and electric field are proportional, linearly proportional. Next, we will talk about force on a dipole. So, let us imagine that So, we will try to understand the force in a 2D setup and then we can generalize it to 3D. So, let us imagine that we have a charge q minus and we have another charge q plus. So, let us call it point 1, let us call it point 2. So, in the xy plane, now the point 1 is at a distance x1 along the x axis from the origin and point 2 is at a distance x2 along the x axis from the origin, and there the distance between these 2 points is a. So, let us define a vector a vector which joins point 1 to point 2. Now, this we can call a cos theta. Now, let us imagine that the electric field is oriented purely along the y direction. So, the value of the electric field at first point is E1y, the value of the electric field at the second point is E2y. So, we can write the electric field to be electric field vector to be E as Ey multiplied by j. So, the force here is the force experienced by this negative charge is F1y, which can be written as q multiplied by E1y, and the force experienced by this is F2y, which can be written as q multiplied by E2y. Now, so F1y is equal to E1y and F2y is equal to E2y. Now, if the field is uniform, that means E1 and E2 are same. In that case, the net force is 0 because these two cancels each other. If they are not uniform, then there is a net force. So, the net force is Fy equal to F2y minus F1y, which can be written as this, and then we can rewrite this expression as x2 minus x1 divided by E2 y minus E1y divided by x2 minus x1. Now, this x2 minus x1 is just this, and which we can write as a cosine theta. So, we can write this as q multiplied by a cosine theta, and if we assume that x2 minus x1 is very small, then this expression can be written as d dE y by dx. And now, this q a cosine theta, this can be written as the x component of the dipole moment vector. Yes, and this is the expression. So, we defined dipole moment vector as q multiplied by a. So, its x component is q multiplied by the x component of a vector, which is a cosine theta. So, it is px, and that is our next net force experienced by a dipole under the assumption that the electric field is oriented in the y direction. Now, this entire expression can be generalized for a 3D case. So, without restricting the electric field to be acting only along y axis, we can generalize it, and the final 3D expression without any assumption becomes Px dx plus Py So, this is the x component of the force plus Px this is j component plus again Px Pz multiplied by the derivative of Ez with respect to z multiplied by unit vector along z direction, and this can be written in a more generic form as, I mean in a compact form as this. So, this force has 3 components along x, y, z, and which we wrote in a compact form as this. Now, let us imagine that there is a volume that contains these dipoles. So, force per unit volume in that dipole can be written as capital P. Here we will use capital P instead of small p, because now we are talking about a volume containing dipole and we are concerned with unit volume. So, it is this. Now, similarly, this also can be written as a component along x, component along y, and component along z. So, Bx, By and Bez are the component of these forces along x, y and z. So, now we will go to moment on a dipole. So, for this we are not going to derive the expression by using similar techniques. We can find out the moment experienced by a dipole as, so we will directly write with for moment per unit volume. And that becomes MP vector is equal to P cross E, and again it can have 3 components. So, we may call them as MEX into I, MEY into J plus MEZ into K. So, that this brings us to the end of electrostatics. Now, we will go to the conservation laws, which will help us getting the constitutive relations. So, first is mass conservation. So, under the assumption that our density does not change, the mass conservation law is simply this: rho into del dot V is 0, or we may write del dot V is 0. So, V is velocity vector which has 3 components: u dot, v dot and w dot. So, this can be rewritten in this way. If I just evaluate the divergence, this becomes this. So, del u dot by del x, del u v dot, del v dot by del y and del w dot by del z, their summation is 0. So, u v w are displacement along x, y and z, and their derivatives with times are the velocities along x, y and z. Okay, next is conservation of linear momentum. So, let us consider a 2D body like this. So, this is our x direction and this is our y direction. Now, this 2D body is of length delta x, its length along x, and delta y is the dimension along y. So, this is the negative x phase where there is a normal stress sigma x x. This is the positive x phase where there is a normal stress sigma x x plus some increment. The increment is del sigma x x by del x into delta x, and there is a shear stress and shear stress with some increment. This is negative y phase where I have normal stress, and positive y phase is normal stress with some increment. Similarly, I have some shear stress and shear stress with some increment. And apart from that, if it is a polarized medium under electric field, there can be force Bex and Bey. We derived it and saw that due to the interaction between electric field and polarization, there are forces, x component is Bx and y component is Bey. Now, if we equilibrate it, if we say that summation of forces along x is 0, then the equilibrium condition gives us that sigma x x plus del sigma x x by del x multiplied by delta x and this multiplied by delta y. So, this is the stress and this stress is multiplied by this length. So, that gives us a force along x direction. Similarly, there would be contribution from this stress, and that is sigma x x multiplied by del y plus we have tau I x plus del tau I x by del y multiplied by del y into delta x. So, this is a shear stress and it is oriented towards the x direction. So, this stress multiplied by this dimension and minus we have tau I x multiplied by delta x, plus we have to add this body force component along x direction. So, it is Bex del x del y. Now, please understand that we are here dealing with only 2 dimensions. So, the dimension along the third direction, which means the perpendicular to this plane, is 1. So, this is our total body force and that is equal to 0. Now, if you simplify this and this cancels and this cancels, and we are left with this equation. And that is equal to 0. Now, this was with the assumption that there is no acceleration. So, if this body is under some acceleration, then this summation of these forces instead of being equal to 0 should be equal to mass into acceleration. In that case, we have to modify this as mass multiplied by acceleration along x, and then right hand side we will have total mass. Total mass is rho into del x del y, because the dimension along z is unity, and that multiplied by del u dot by del t, and similarly we will have the same thing here. So, rho del u dot by del t. So, that is our conservation of linear momentum along x direction. Similarly, along y, this equation can be written as tau x y by x, a partial of tau x y with respect to x, del sigma y y by del y plus b y is equal to rho del v dot by del t. Now, this can be generalized to 3D. So, in 3 dimensions, if we want to write it in a compact form using the indicial notation, we can write this as so this is the equation for the ith direction. So, I here it can be x y z, similarly j also goes from x y z. Now, here we considered only one body force, and that is due to the polarization and electric field. Now, if there are any other source of body force B I, that can be from any other source, in that case it has to be added to it. So, this was about conservation of linear momentum. Now, we will go to the next one and look into the conservation of angular momentum. So, we have the same diagram, and here, so this is our x and this is our y. Now, here apart from this we will have a body moment which is m e z. So, this is x, this is y, and z direction is perpendicular to the plane. So, with that direction the moment is m e z. So, that is also going to be there. Now, if I first satisfy the moment equilibrium, so after satisfying moment equilibrium we get this. So, the way we satisfied the force equilibrium, we can satisfy moment equilibrium also, which we are not going to do in details. We will only write the outcome of that satisfaction. So, it becomes tau y x minus tau x y is equal to p x e y minus p y e x. So, remember the moment experienced by this polarized medium is, unit volume of the polarized medium is P cross E. So, if I take the cross product and take its k component, we get the expressions in terms of P x E y and so on. So, this is what we get. So, we get the expression in terms of P x E y, P y E x, and this is what we get by satisfying it. Now, if I generalize it to 3D, we get 3 of such equations. We get 3 such equations, and those equations are the first equation itself that we wrote, and then we have tau zx minus tau xz is px. Okay, so we have to put E as the way we have put E. So, this becomes Px multiplied by Ez minus Pz multiplied by Ex, and then we have tau Zy minus tau Yz, and that is equal to Py multiplied by Ez minus Pz multiplied by Ey. So, that is about the conservation of angular momentum. However, in our case we would neglect the nonlinear terms appearing because of this polarization and electric field in both the angular momentum equation and the linear momentum equation. So, from the linear momentum equation we will neglect the BE terms, assuming that our electric field is uniform, and also here also we will neglect these terms. So, if we neglect these terms, our stress matrix becomes symmetric. So, when we neglect these terms, it becomes tau Yx equal to tau Xy, tau Zx equal to tau Xz, tau Zy is equal to tau Yz. In that case, the stress matrix becomes sigma xx, tau xy, tau xz, tau yx, sigma yy, tau yz, tau zx, tau zy, sigma zz. Now, if this and this are equal, this and this are equal, this and this are equal, we have 6 independent terms. So, that way we can simplify it and write the stress as a vector. So, it becomes sigma 1, sigma 2, sigma 3, sigma 4, sigma 5 and sigma 6, where this is sigma xx, xx, this is sigma yy, this is sigma zz, this is tau yz, this is tau zx and this is tau xy. Now, we will talk about the thermodynamics laws. So, our constitutive relation should satisfy the thermodynamics laws as well. So, we will start with the first law. The first law in the rate form can be written as du by dt is equal to w dot plus q dot. So, du by dt is the U is the internal energy and du by dt is its time derivative, and w dot is the rate of work done on the system and q dot is the rate of heat supplied to the system. So, for our piezoelectric medium we can write this as sigma ij multiplied by epsilon ij dot plus E as in electric field multiplied by di dot plus rho gamma minus q I. So, here are two more terms. Gamma is rate of heat supplied from internal sources, maybe any internal source per unit mass. So, it is per unit mass, and q is our heat flux vector So, q I comma I just signifies del q by del x plus del q y by del y plus del q z by del z. So, it has three components q x, q y and q z, and this quantity is time derivative of internal energy per unit volume. So, here the work done comes from these mechanical quantities and the electrical quantities, and this contributes to the heat. Now, the second law of thermodynamics, written in the form of Clausius-Duhem inequality, is T s dot plus T multiplied by Q by T comma I minus rho gamma, which should be greater than or equal to 0, and here S denotes entropy. So, with these two laws we will conclude the discussion here. So, in the next lecture we will combine the two laws and gradually move towards the constitutive relation formulation. With that, let us conclude. Thank you.